Okay, good afternoon, everyone. It's a great pleasure and honor to be here as a past recipient of the fellowship from the foundation. Again, I'm Mingo Seok from Columbia University, and my area of expertise is actually integrated circuit and system design, which may or may not sound familiar to you. But basically, I can say this: my job is basically dealing with how to design chips in your computers or laptops or cell phone or other electronics, something like Intel microprocessors in your computers or ARM cores in your cell phone. So today I'm going to talk about one of the important trends in the integrated circuit and system design, which is to reduce power consumption a lot for some of the emerging applications. So every presentation given by the circuit designer cannot start without the slide on the Moore's law. Basically, for the last 40 years, the number of the transistors that we integrated in a single chip increases exponentially. So in 1970, Intel first produced a chip called 4004, which is 4-bit CPU integrating 2,300 transistors. And after 40 years, in 2013, Intel produced a chip called Ivy Bridge, which is quad-core 64-bit microprocessor integrating 1.4 billion transistors on a single chip. So what does it mean to integrate such a large number of transistors on a single chip? That means that you can all enjoy extremely high-performance computing machines with a very affordable price. For example, you can buy these billion transistor chips only with a few $100s. So as compared to the Moore's law, I'm not sure how many of you are familiar with the Bell's law. So Bell's law is simply stating that the volume of the computer systems has been reduced by 100 times in every decade. So in the 1960s, people invented mainframes which can easily fit up multiple rooms to compute some of the mathematical problems. But after 10 years, people developed mini computers which can fill only a fraction of the rooms. And this trend to miniaturizing the computing system has been continued for the last 40 years, from mini computers to workstations, from workstation to the personal computers, from personal computers to laptop, and laptop to smartphone. So natural extension of this trend is ubiquitous computers. Given that the smartphone currently takes about 100 cubic centimeters, if we improve the volume by another 100x, the ubiquitous computers can be as small as 1 cubic centimeters or even smaller than that. So two important technical questions would be, can you actually make such miniaturized computing system which is as small as 1 cubic centimeters or even below that? And if we can do that, what can we do with such miniaturized computing systems? So if you are early adopter of the electronics, in fact, you are already seeing some of the computing system that is miniaturized. So, for instance, Nike started to selling the product called Nike Fuel, basically tracking the number of the steps you made per day and send it to the information to your cell phone and basically for your review. And Fitbit, which is another startup, also produced the product called Flex. This is the bracelet. And this one can do multiple things, including counting the steps, and distance that you walk, and calories you burnt, and the multiple things such as like sleeping hours and so on. And Samsung recently also produced the watch-type electronics, which can do multiple things, including making hands-free callings and so on. And Google Glasses, which is produced by Google, doing even more ambitious stuff, like navigation, real-time workout, and message sending, taking pictures, and number of things. So another big applications of this miniaturized computer is the Internet of the Thing. As some of you are already familiar with, Internet of the Thing is the vision, basically to extend the network into the object that used to be not connected to the network, such as your phone, such as your cat, such as your wallet or keys, cars, or anything that is not networked yet. So So there's a full spectrum of the IoT evolutions, including object indexing and where it is, knowing where it is. And also, at some point, we expect these objects actually start to talking to the networking hub and also interacting with each other to do some intelligent task. So some of the consulting firms consider the market of the Internet of Things worthwhile to tens of $trillions, which is a huge amount of money because big electronics companies, the yearly sales is around less than 1 trillion, actually much less than 1 trillion. So this is the huge market. And there's so much more things that we can do with these miniaturized computers, which is less than one cubic centimeters. For instance, robotics, especially the micro robots, are emerging for a variety of applications, including the surveillance, infrastructure monitoring, logistics, and manufacturing. All of these robots need a certain amount of computation ability on board for control and digital signal processing. Implantable medical device is another example, which can real-time monitors various biological signals and detect abnormality and actuate if needed. And the other thing that we must talk about is the brain-machine interface, which is the vision that creating the electrical connectivity between your brain and computer requires the key technology to develop a very small computer system which can detect and pre-process and transmit brain signals to the outside world. So as a circuit and system designers, what kind of things needs to be done in order to develop such a miniaturized computing system? So I call it as call those challenges as 322 challenges. Basically, we need to improve 3 qualities in microsystems. First one is the performance and lifetime form factor. Performance means basically you need to finish certain tasks within a deadline. Also, you need to add more functions or more features through the more hardwares or softwares. Lifetime is also very important. First of all, you don't want to replace the battery or recharging the battery too often. And also, you want to use the energy harvesters and so that we can actually give the energy autonomous to the computing system. Finally, form factor is very important for facilitating the deployment, as well as the enabling new applications that only the small computing system can enable. So ideally, you want to improve all of this, but in reality, it's very hard to do. So there's always trade-off. So there's a 2 trade-off. First one is the performance versus lifetime. So if you try to improve your performance of the computing system, let's say by increasing the clock frequencies or adding more memories or computing hardwares, then you end up with spending more powers, and that hurts your lifetime. Similarly, there's the trade-off between lifetime and form factor, meaning if you want to increase your lifetime, the simplest way is to add more battery. But apparently, this adding battery hurts your form factor because battery usually takes the dominant area or volume of your computing system. So there's a very simple 2 directions that you can try. The first one is the electrical system design point of view to reduce your power consumption while providing still good performance. The other way is the energy storage technology by increasing their density to store or generate the energy. So speaking of the energy harvester is a very important technology for those miniaturized computing systems because it can enable near perpetual operation if your computing systems consumes less than the power that this harvester can generate. So there's a lot of work for the last tens of years, and some of the promising modality for these miniaturized computing systems are thermoelectric, kinetics, and the photovoltaic. And if you want to build a centimeter scale or even smaller systems and use one of these technology, your average power generation density over 24 hours will be around 10 to 13 microwatt per square centimeters. So if you make the system that consumes less than 10 to 13 microwatt, that means you can make the systems to operate near perpetually without any replacement of batteries or maintenance. So if you want to make the even smaller system, let's say millimeter scale, then your power budget becomes 10 to 30 nanowatt per millimeter scale, which is extremely low level. So where we are, so what's the power consumption of today's microprocessors? So this is the specification table from the ARM, and they're one of the most energy efficient microprocessors called Cortex-M3. When it is implemented 40 nanometer technology, this one consumes about 7 microwatt per megahertz. And this number is not including the memory powers as well as the peripherals. So once you're adding all of this, your power consumption is roughly 20 microwatt per megahertz. And if you can learning this at 10 megahertz, which is not great, but sort of acceptable, your power consumption could be around 200 microwatt for 10 megahertz. So as you've seen in the last slide, the centimeter scale energy harvesters can produce about 20 microwatt or 30 microwatt. That means the gap between the current state of the art versus the power level that we want to make this such a small computing system is around 10x. So if you improve by 10x your power efficiency of the microprocessors or other electronics, you can actually make these miniaturized systems that can almost perpetually operate without any battery replacement and anything. If you want to reduce the volume even to the 1 millimeter size, then you need improve another 1000x power efficiency, which may sound very challenging, but this is not totally impossible. So this is sort of the research, main challenges that we try to tackle, how we can reduce the power consumption of the microsystem design. So we're looking at a bunch of techniques in fundamental design level techniques, as well as some of the sub-blocks and some of the bigger blocks, and finally some of the integration systems like these three examples shown here. So I want to explain some of the technologies that we did to reduce the power consumption substantially. So one of the main techniques that we use is the ultra-low voltage design. Nominal supply voltage of today's integrated circuit and system chips are usually 1 volt. But you can actually scale down the supply voltage if you can tolerate the delay. So by doing so, you can actually save the energy quadratic manners. And if you, for instance, if you're scaling supply voltage from 1 volt to 0.3 volt, you can reduce the power consumption by almost 10x. Another important thing that we need to take advantage of is the duty cycling. So because most of the applications and those systems has a quite low duty cycles. For instance, if you want to measure temperature in every 10 minutes, your active time is only between 10 to 100 milliseconds, and most of the time of the microelectro systems will be consumed or spent while it is in the standby mode. So the total power consumption tends to be dominated by the standby power, and if you can put this system into the sleep mode, you can reduce the power consumption substantially. So based on these simple techniques, or simple but fundamental techniques, we developed our first chips using those two techniques. And this is called, we name it as the Phoenix processors, and this includes some of the CPUs and memories and the sensors and timers and so on and so forth. And this chip is fabricated, and we measure the power consumption, and the power consumption is 30 picowatt during the standby mode, and 300 nanowatt at active mode. And if you consider very low duty cycle of 10 to the minus 4 to 10 to the minus 5, we can achieve average power consumption of sub-nanowatt. So this enables actually millimeter scale system. For instance, this entire form factor is 1 by 1. So the chip size is 1 millimeter square. And if you stack batteries of 1 millimeter square and stack on top of these processors and just bond, then you basically enables multi-year lifetime, for instance, 10-year lifetime, without replacing any batteries during that operation. So recent years, there's quite a bit of demonstrations to reduce, these ultra-low power microprocessors and SoC. And this plot basically showing that the performance of the microprocessor or SoC and the energy efficiency of these beakers. And it's better to be large. And these black dots represent some of the commercial off-the-shelf product, such as like TI's MSB 430 and Atmos and Cortex. And these red dots represent some of the research beakers using low voltages and variety of the low power techniques. So as you can see, these research products can substantially improve the energy efficiency by 10x or 100x. But at the same time, these processors running much slower because you reduce the VDD and there's no pre-launch to improve your energy efficiency. So that's the important challenge. So how we can improve performance without hurting the energy efficiency? So that sounds very contradictory because in the beginning of the presentation I told you that the performance and efficiency are in trade-off. So that sounds a little bit contradictory, but in fact we can do that by using some of the smart techniques. For instance, we explore some of the architecture level techniques called the pipelining, as well as the parallelisms and many other techniques. And the key ingredient is by using these techniques to improve the speed, actually turns out to be reduce the total, leakage energy consumption. The leakage energy consumption is leakage power integrated over the cycle time. So if you actually reduce the cycle time, you can reduce the leakage energy consumption. And overall, even if these techniques adding some of the power from extra hardware, but actually you reduce the leakage substantially, so your energy consumption can be lower as well. So all these techniques can improve speed as well as the leakage at the same time. And we employ these techniques in the FFT core, which is shown here, and in IC design. And we achieved the world record in energy efficiency as compared to the previous state of the art. So more specifically, these processors, these cores running at 270 millivolt, consuming about 15.4 nanojoule per FFT, and producing the FFT at 240 megasamples per second at the clock frequency of 30 megahertz. This is 10x more faster than and 2.4 times higher efficiency than the previous state of the art. So one secret that I didn't tell you so far is all the performance and efficiency number that I mentioned is measured only at the typical condition, meaning room temperatures and average process variation and ideal voltage sources and so on. But in reality, all these conditions varies, and all these varying conditions create a variability in the performance and the efficiency of the chip. This is the big challenge in the semiconductor industry, and a lot of research has been ongoing to solve these problems. And for instance, the conventional way to tackle this problem is the worst case design. This makes everything very simple. The only issue is very wasteful. For instance, if you design a microprocessors and the delay is, let's say, 1, and by assuming some of the worst case condition for like operation temperatures and voltage and process variation, you actually have to delay your clock frequency by 45%. So your delay becomes 1.45, so you're already having lots of margins in today's electronics design. And this problem is even greater if you reduce the VDD. For instance, in this case, you reduce the VDD to 350 millivolt, and now the margin becomes about 362%, so which is a lot. So we can't really do that because this margin is too prohibitive. So what we did is actually we come up with some of the smarter techniques saying in situ error detection and correction. So this one basically automatically detects the correct errors while the processor is running, so there's no need for the timing margin. And this technique is demonstrated in one of the small microprocessor called R processors. And this one, as compared to the margin design, operating at the same supply voltages but with a margin, the new design achieves the 2.6 times better energy efficiency and 5 times fast throughput. So that's all about the digital system, but we also have a lot of analog systems to reduce the power because if any of these dominate the power consumption, then total energy efficiency cannot meet the requirement imposed by the energy harvesting unit. So we also working on quite a bit of the analog component. This is one example, basically voltage reference to provide the constant voltage across temperatures and process variation. And we come up with some fundamentally different structures and reduce the power consumption substantially as well as the area and voltage scalability as well. This is commercially licensed and actually lies in the commercial product. So we are very happy about it. And we also design some other things like regulators and voltage temperature sensors, or improving area or efficiencies, as well as the voltage scalability. So I have only 2 slides left. So let me summarize. So we work on various techniques in circuit and architecture and system level to reduce the power consumption for centimeters and millimeter scale energy constrained systems. And we sort of demonstrated that extremely energy efficient circuit and systems are viable with the orders of magnitude improvement in energy efficiency. And numerous applications for centimeters and millimeter scale computing systems, including the wearable electronics, Internet of the Things, medical implants, micro robots, and so on and so forth. And there can be even more apps that we haven't found yet because Facebook wasn't there when we first invented Internet. And in order to enable all of these wonderful application, energy efficiency is the key while addressing all the complexities caused by these energy saving techniques. So let's go back to the history, and for the last 40 years, we working a lot and invest a lot of money to create these computing machines that is 1,000 times faster, or even actually more than that, by having more cores and so on. This direction is still very important because even if the computer stays so fast, in order to achieve the really ambitious dream like AI, we need a still computing power that is orders of magnitude higher than the current level. But at the same time, we need to spend a little bit more effort for the nanowatt lace for the next decade to enable all these applications. So that's all I have. Thank you for your attention.